Welcome, everyone, to today's Tech Talk. My name is Jeff Walls. I have the pleasure to introduce our speaker today, Noam Nissan. Noam is going to be, we're very fortunate to have Noam Nissan as a visiting professor for this academic year. He's a professor at Hebrew University in Jerusalem and will be spending the 07 and 08 academic year at our Tel Aviv office. Noam received his PhD from UC Berkeley in 1988, studying under Professor Richard Karp. He's a well-known and leading researcher in the area of electronic marketplaces and auctions, as well as economic mechanisms in computation. Noam will speak today about algorithmic mechanism design. So please join me in welcoming Noam Nissan.
Thank you. Okay, so what I basically want to talk today is about my research prior to Google. So this is all academic stuff, nothing about what I'm doing here. And basically, I'm trying to give basically an overview of a field that a bunch of researchers, not a very large group, but still a significant number of people, have been working on for maybe about 10 years. I will start actually by trying to describe what we're trying to achieve. What is basically the problem that this field tries to address? Once I try to lay out the problem, then I'll have to spend a little time talking about what kinds of solutions are we talking about? What is the language that will allow us solutions? Because basically, we're actually going to use ideas and notations from macroeconomics to actually solve computer science problems. So this is, if you wish, the opposite of what companies like Google or any company that does any kind of electronic commerce does, which actually uses computers to solve economic issues of how to best match advertisers, let's say, to publishers or any other kind of electronic commerce. We're actually going to use, in this talk, the economic point of view to actually solve standard classical, I would say, computer science problems, but of course in this new setting, which I will describe. So once I describe the language of the solutions, the type of solutions I'm looking at, I will describe, if you wish, the basic solution. So there's a basic positive result from economic theory that is going to be the starting point for any further investigation in this field. I'll describe it. And then I'll say, OK, so what are the challenges when we actually try to bring this economic theory into the computer science point of view? And then these areas will be where the interesting progress within computer science has been made about these issues, and of course where there is lots more further research, open problems to be done. And I will give a lot of examples, or a bunch of examples, showing the different type of issues that arise when you want to do it. So let's take a high-level view about the internet. So in the internet we have lots of computers. They're interacting all the time and doing lots of things. So when I'm saying doing lots of things, I'm looking at all levels, if you wish, of the communication protocol hierarchy. From the lowest level questions, this computer is sending a packet to this computer through this router, to the high-level issues of, they're actually trading. This guy is buying stuff and selling stuff over the internet, and all levels in between. And so if you look at the internet at this point of view, well, you could say it's just a very big distributed computer system that computer science researchers have been working on for a very long time. So that's nice. But it seems that since the beginning, the early days of the internet, of the splash of the internet, which I'm talking about maybe 95 or so, people realized that there's a new ingredient that's very, very important in the internet and was not really addressed by computer scientists significantly beforehand. And this is the fact that the different computers belong to different people, different organizations, and these computers will be basically probably do not what any kind of protocol some engineer comes up with and tells them, do this protocol, but rather what's good for their company. So I'm not talking about issues like faulty computers or malicious computers like in cryptography or in cryptography or various Byzantine kind of things, but just the normal computers that belong to normal corporations who want to do what's good for them. They want to send their data faster. They want their access to be better. They want to buy stuff cheaper and sell it more expensively, and so on. And this is a standard way that things work on the internet. You don't have to be malicious in order to optimize your computer to improve your own revenue, your own goals, your own speed, your own communication bandwidth, whatever you are trying to optimize. And no computer science, and basically computer science protocols were never designed to work under this environment. When you have actually selfish interacting computers that do what they want or what their owners want really, rather than some protocol. So if you're actually looking at all the classical internet protocols, IP, TCP, let's look at TCP for example. TCP does not really work, if you wish, when the different participants are selfish. There is a very easy thing that can be done to actually, let's say, improve my computer's bandwidth, latency, everything, all the communication aspects of it, by tweaking slightly the TCP code in my operating system, actually telling it not to be considerate of other users as the TCP protocol mandates it should be, and that would improve my own communication noticeably, I mean significantly in fact, of course hurting all others. If all others do the same, then everyone is worse off. But if only I tweak my own TCP algorithm inside the operating system, I can actually improve significantly my own communication. So that's because TCP was designed for computers that all execute what someone told them to execute, the right protocol. And the question is, what do you do? How can you handle, general level, higher level kind of things, higher level kind of issues when the different participants are selfish, doing what they want? By the way, if there are any questions, please do stop me and I'll be happy to answer. Right. Okay. So the idea is if you're actually trying to design mechanisms, design protocols for this environment with selfish users, we're trying to design what's called incentive-compatible mechanisms. What is incentive-compatible mechanisms? Mechanisms that basically give incentives to the different participants to act as instructed, rather than trying to manipulate the different protocol to their own advantage. So, and we're not going to assume that we have to somehow assume something about what they want, because if we don't know what they want, they may as well be malicious, and then we're back into the world of cryptography, where basically they can kill anything. I can't have any meaningful interaction with a malicious computer. But we're not talking about malicious people, but rather with people that have their own goals. So we're going to have to, formalize or study it in some sense, and we're going to assume that they are what's called rational. So being rational is a very technical and narrow term here. Just means that they have their own well-defined goals, and they are literally only trying to optimize their own well-defined goal. Okay? So they have some kind of, we usually talk about utility function, a function that specifies how happy they are with what the outcome of any protocol that they are involved in. And they try to actually improve their utility, improve their happiness. And a mechanism basically is allowed to do one other thing beyond just being a computer protocol, a distributed protocol. It allows to charge payments from the participants. So it is completely clear that if no money is involved, it's going to be very, very difficult to convince people basically not to hurt others if they're only trying to optimize their own goal. So we will actually have some kind of notion of money. So each of our protocols will be some kind of computation and it does something, and then it also specifies who needs to pay what and to whom. And our basic assumption is the following, that what each one of the participants is trying to optimize is basically the value that he gets from the outcome of the protocol minus the payments, any payments that he makes. And if he gets money, that's going to be simply, of course, a positive term. And the key idea that we want to get to, we want to have a mechanism, we will call it incentive compatible, and technically it's also sometimes called truthful or strategy proof. Basically, if rational players will not manipulate it. So basically, if the payments together with the outcome provide incentive to all participants to always participate correctly in the protocol. So when we are talking about participate correctly, the real issue beyond everything, below everything, is really their private data. So if all the data was public, then it's completely obvious that we could just say, okay, here's the data, here's the required output, we don't ask anyone to do anything. The whole problem is that information is private, and really what's important is that actually computers behave according to their true private information, and not according to some made-up private information that would improve their lot. If they behave completely in a way that's not consistent with the protocol, that can, of course, immediately be caught. So what we're interested in not behaving in a way that's consistent with the protocol, but according to some false, wrong input. So before I go and talk about, try to formalize it, let me give you a very classic example that I suppose most of you already know, but look at it in these terms. So here's the problem. Classic, if you wish, problem. There are n different computers or bidders or processors, it doesn't really matter, that want to use a single communication link. So you can think of it, for a single packet and a single picosecond, or you can think of it like reserving enough bandwidth and a quality of service kind of thing. And only one of them can get that link. And the question is, who gets it? Now, we don't want to just arbitrarily give it to one of them, but we're going to assume that there is some kind of inherent value. So it's not that all of these are the same importance, but there's a different value for each one of these bidders, I'll call them now if you don't mind, an inherent value for the bidder for actually getting his transmission. And of course, what we would like to do is give it to the guy who values it most, to actually find the most valuable transmission to actually give the link to. So in the old world, this is a very simple protocol. Everyone tells to, let's say, our allocator, how much is it worth to him. The allocator chooses the highest value, and then he gets the link. It's very simple. But of course, now suppose that the different computers belong to different participants. If they know that this is a protocol and no payments are involved, then it's very easy to know what will my computer do. Instead of actually reporting my true value for the link, I will report 1,000,000 or extremely high value. And of course, everyone else will do the same, and the result will be totally meaningless. Okay? So how do we deal with it anyway? The first thing you might think is actually, okay, let them, if they declare value, let them actually pay the amount that they declared. So now VIs are going to be dollar values. And if you say that this link is worth to you $3, then pay the $3. The other guy says $5, he will pay $5. And now at least it seems that people will tell the correct thing. But you see, again, people won't really tell the correct thing. So suppose that my value is $5. If I say $5 and I have to pay what I said, basically my resulting utility, net utility, is 0. I won't say 5 if my real value is 5, because then I'll be left with nothing. I will say slightly less than 5. How much less than 5 really depends on the competition that I have. If I know that the next guy is 3, then I will definitely say 3.1 or 3.01. But if the next guy is 2, I will say 2.01. And if I don't know, what will I do? I will have to try to guess, to do some kind of statistical analysis, optimization. But then, of course, I may be wrong. And because each of us is doing all this, all this kind of analysis, and these analyses are connected in some kind of weird game theoretic way, it's going to be pretty difficult to always know who wins and to make sure that the guy who wins it actually is the one with the highest value, which is definitely not the case in general. Okay? So what can you do? So the really amazing idea that Vickrey had back in the 60s, for which, by the way, got a Nobel Prize, was to use the second highest price, the Vickrey auction. Basically, the highest guy wins, but the price that he pays is the second highest price, the second price of the second highest competitor. So what is so good about this? Well, the really interesting thing is that you can actually very easily prove a formal mathematical theorem that no bidder can ever gain whatever the other bidders' values are or whatever the other bidders report. No bidder can ever gain by lying. You are always better off, or at least as well off, by telling the truth, by behaving according to the real value. So let's just look at the basic idea. So the formal proof is really easy. You can go, and if you've never seen it, you should actually go and prove it to yourself. Basically, suppose my real value is 5. How can I gain? Well, suppose that the second highest value is 3. Well, if I say more or less than 5, nothing is going to be changed because the value, the number, the amount that I pay is basically the second highest bidder, which does not at all depend on what I say, but rather on what the other guy says. So the only way that a difference can be made if I actually say something that is below 3, below the second highest, in which case I will lose. But then I don't want to lose. So I can never gain, basically, by lying, and this is a formal theorem. So, first of all, this is used lots of times. But if you look at it from a computer science point of view, we've achieved here something that's quite remarkable. We were able to correctly compute a function. The function is who has the highest v, where we didn't have any access to the inputs. The inputs were simply distributed to the different players. The different bidders had no interest in getting the right result, but just had their own selfish goals. And yet, we managed to get the right function, to compute the correct function on inputs that we didn't know. So if you look at it, this is really quite amazing. And if you look at it from economic point of view, this is already, if you wish, the basics of Adam Smith's invisible hand, by which you get the right allocation in society. Even all the different members with their private information are totally selfish. Okay? So now let's try to generalize this thing, and let's put it this idea basically in the most general framework. And here is a general formalization of this idea of incentive-compatible mechanisms for various problems. So we're going to have a set A of, if you wish, so what we will call social alternatives, which is basically, usually in computer science, we're talking about allocating all the different resources that the protocol studies. So we're looking at all the different possible allocations of all the resources, all the possible outcomes of the protocol. Of course, this may be exponential in whatever you want it to be usually. So the total number of allocations can be totally huge. But for mathematical formalization, it's convenient to look at just a finite set A of possible outcomes. Now, each player looked at all this huge outcome and had some kind of idea how good is this for you. And this is going to be we're going to call it their valuation function. So it basically assigns to each outcome a number that says how good is this for the ith player. And now, usually, this function will not depend on the whole outcome, but just on the part, if you wish, of the allocation that the user gets, or maybe a few other neighbors in some ill-meaning sense. But still, there's going to be some kind of function this way. And now, what does the mechanism do? It does two things. Given the inputs of the players, which are completely, so the idea that the inputs of the players are now completely encapsulated by these valuation functions. So usually you won't actually send the valuation function, but only the parameters, the private parameters that are actually specifying it. But mathematically speaking, we get these valuations. We apply some kind of function that says, if these are the different preferences of the different members of society, the different bidders, what is the output that is going to happen? So this specifies how do we actually want to do the allocation, what do we actually want to be the outcome of the protocol when the input, if you wish, when the private values are as given. And of course, it also is allowed to actually charge payments from the players, just a dollar amount, where I recall again that we're assuming that everything now is in the same monetary terms. And the formal definition of incentive compatibility is that you never gain by lying. So what does never mean? Even if you knew all the information in the system, which is a strong if, but even under this assumption, you will never gain. So this really means that you never can gain. So let me actually look at this. Let's try to see what this means. It means that if you look at any player I, whatever the true inputs are, whatever the current situation, whatever the values of the players are, the valuations of the players are, if player I thinks, shall I maybe act according or report some other valuation, which is not my true value, but because my true value is VI, what will happen if I actually report a VI prime? Will this improve my lot or not improve my lot? So if he reports the right VI, there's going to be some outcome which is going to be A, and he's going to get a value of VI of A from this, and he's going to have to pay P, where P is the amount that he pays when he reports the right thing. So A is defined simply as the outcome of the mechanism when you actually report your true value A, and P is the payment that the mechanism specifies if you report your true value A. Now, let me just say this notation is standard in game theory and not all used so often in computer science. It's very, very convenient. VI, V minus I simply means the vector of V's. So it's V1, V2, V3, V4. V minus I just means when you take out the ice value, the ice component from it, and then when I have VI here, I put it back. So this is simply a way to focus on a single component versus the rest of the components. So this just means the V with the all correct V. And I'm going to compare this to what happens if I lie, if I act according to some other valuation. So if I act according to some other valuation, the other players are still going to say what they're saying. I will say this. The outcome will be this some kind of allocation A prime and some kind of price P prime. And what I want is that if I compare my utility, how happy I am while saying the truth, versus how happy I am when lying, it's better to say the truth. Okay, so a mechanism that has this property basically gives no motivation for any player to ever say something other than the truth, other than acting according to his completely true private information. Okay, is this clear? So let me just say a few comments about the definition. So first of all, it was very strict. It was formally it's what's known as dominant strategies. It means that whatever the other players have, you can't gain. One can also look at a much weaker and more natural, if you wish, assumption that's saying, well, of course, you don't know what with the total situation. You just have some kind of, you have some kind of maybe probability distribution that specifies your lack of knowledge. Let's see, can you actually improve your lot even with this partial information? And of course, the result, so of course, the definition we have here is much stronger. If you can never improve your lot by lying, then of course you can't improve your lot by not knowing anything, by not knowing everything as well. The second thing is that this is a very clean definition, meaning you can never gain. You can also think of various weaker notions, or you can't gain too much, or you can't gain computationally efficiently, or you can think of many other weaker variants. And this is, of course, a very reasonable class. Actually, this is maybe the name of the game to find the right notions here. So it's really interesting field for research. But for this talk, I'm just going to focus on the completely clean definition, never gain by lying. And the third comment is that this idea of telling the truth, at first sight, it may seem a bit overrated. What do I care if they tell the truth or act according to something else? Really, the only thing that interests me, there's going to be some kind of weird mechanism. At the end, there's going to be an outcome. If players are selfish, they're going to act according to whatever optimizes their own goal. So we have like a game situation kind of thing. So let's find the Nash equilibrium or some kind of equilibrium notion. And let's just require that the outcome under this equilibrium is what we want, rather than forcing them to tell the truth. So this is the basic idea. And it turns out that this more general definition basically is exactly equivalent to gain nothing, basically, in the parameters that I'm studying today, if you allow these more general things. Whatever can be reached at equilibria when players are selfish can be reached, by the way, if they're telling the truth. And this is as long as the equilibrium condition is still under this universal thing that we defined here. So that basically the definition so far was basically a classic definition from the economic field of mechanism design, and more or less with the standard notations. So when does this become what's called algorithmic mechanism design, this new field that actually combines computer science together with a microeconomic theory? Well, basically, when you have a mechanism design kind of challenge, but in an algorithmic context where there are some algorithmic problems, algorithmic challenges in actually finding the outcome. And then you really have to combine both the computer science point of view and actually finding the correct outcome, social, if you wish, social welfare, and combine that with all the economic issues of finding the right pricing as to make the incentives behave the way that you want. So here are a bunch of classical examples that fall squarely into this category. One of them is called combinatorial auctions. Suppose you have a bunch of things that you want to allocate together. So the classic example is the Fcc auction, where they have hundreds or thousands usually of licenses. And all of these licenses are related to each other. Some complement each other, some are substitutes for each other. Thousands of licenses in different frequency bands, different geographic areas, and they're selling them together. And the different bidders, are all interested in subsets of these. And the question is, how do you allocate all of them amongst all the different bidders? So if you look at it as a computer science pointer problem, it's already hopelessly difficult. It's, of course, NP-complete any way you look at it, so the allocation is difficult. Even specifying what you want is like a language design issue, which is not trivial. It's very complicated. And then how you combine that with incentive issues, with what are the right prices. Okay? So this is one example. Another example is scheduling. So usually in the scheduling literature in computer science, we have a bunch of processors, and we just tell just this job run here, this job runs there, and then of course we still have all of our classic scheduling problems. If you want to optimize the make span, what do you do? If you want to optimize this other thing, what do you do, and who runs what? But what happened is the computers now belong to people. They're not just willing to run your process. You sort of have to pay them for that because they are selfish entities. They're like servers, commercial servers running and willing to execute other people's jobs. How do you now do it? So you're left with the usual scheduling problems, but now you also have to pay them in an appropriate way. Another example is lots of times there is something that's done collaboratively in the internet. For example, a simple example is you have some kind of multicast. So multicast is often better than actually sending a separate message to each and every different computer, definitely when you're doing like a video kind of thing. If you're actually doing a multicast, how do you actually split the cost of transmission, which is now can't be really specified who is responsible to which part of the transmission, because there's a multicast, there is some kind of common thing there. How do you split it between the different guys who want to receive the transmission? So again, there is an algorithmic challenge there, who gets it, where do you route things, and so on, the usual computer science kind of thing. But also the question is pricing. How do you make sure that actually the guys who really need the transmission get it and not the others? And many other examples like this exactly squarely fall into this category. Almost any kind of thing you want to do on the internet, if you really think about it, you're left with a messy computer theoretic problem as well as with a messy economic problem, and they are related to each other, interrelated. You can't solve each one of them separately. So in general, the holy grail, if you wish, what would you in general want to do? Basically, we'd have all the resources over the internet. So every single byte of memory, every single cycle of CPU time, disk, a communication link, a printer, any other hardware that happens to be connected there, that all belongs to the internet. Each piece belongs to someone else. And now we really want to somehow reallocate all the resources in the world in the optimal way among all the different uses. So there's no reason that I would have a printer if your printer is just down, just the next house, and you're willing to let me use it, for example, for a fee, of course. So in general, these are the type of questions, well, this is like the extreme form of it, of course, but these are the type of questions which we would want to address in algorithmic mechanism design. So let me start by saying, here is what we learned from the economists, which is a very neat trick, and it is the starting point of every investigation along these lines. So what we learned from the economist is what's called the Vickrey-Clark-Groves mechanism, and here's a simple way to describe it. Okay? So the first thing is, this is applicable when we want to optimize what is probably the most natural thing to optimize, although not the only one from our point of view, which is the sum of the values of all players. This is sometimes called the social welfare. So if I want to optimize the sum over all participants of the value that they get from the allocation. Okay? This definitely makes a lot of sense. And what do you do if you want to do that? Well, economists don't worry about how do you find the allocation that actually maximizes this. You just find it, so let us just find it. So you find the allocation A, the outcome, that is best from the total social welfare point of view. And now the only question that we have is, what kind of payments do we charge people as to make them tell the truth about all their values? And here is a basic idea. And the basic idea is as following. Let us pay to each player I the sum of the values of all other players of the given outcome. Okay? So if for this outcome, I say my value is 5, you say your value is 7, you say your value is 2, I will get the 9. 7 plus 2. So the mechanism, this centralized fictitious entity, will pay me 9. Okay? So don't worry for a second the fact that we're paying, so as a mechanism is paying so much money to the bidders, where actually they should be paying to it. But let's just see, why does this very simple scheme actually ensure that we get the correct result, that no one ever wants to lie? Well, basically, now let's look at it from my point of view. How much do I get if some outcome A actually results? Well, first I get my own value of that result, which is Vi of the result. But then I'm also going to get paid all the values of the others. So my total value is going to be simply the sum of the values of everyone, including myself and others. Each one of us counts as once. That's I'm going to actually get exactly the sum of values of everyone of that result. Which means that really what will optimize my own welfare, what is best for me, simply saying the truth, which will result in exactly the A that maximizes this being chosen. Okay, because now basically we've completely aligned my own interest and the society's interest, which is basically what the mechanism is trying to achieve. So there's no reason for me to lie. My interests are exactly to find the most socially optimal thing, so I will never lie if I'm rational. So this is a basic idea, very simple idea, and yet very powerful. So one thing for those worrying about, we're paying all this money to the players, they should be paying us. The actual thing is that there's another term that I'm going to detail in a second that's going to have no strategic justification. So that other term is not going to be important at all from my point of view when I consider my own incentives, but will sort of fix the direction of payments. So what is not going to make any difference from my point of incentives? Basically, if the prices that I get paid are increased for every possible auction, or increased, let's say, by 5, nothing has changed for me, because then I'm comparing two numbers that I can get for two different alternatives. Both of them have increased by 5. Now, this 5 can be an arbitrary function of almost everything except what I say, because it can be an arbitrary function, let's say, of what the other guys said. Because, again, when I am looking at my own incentives, that's going to be a constant, and whatever I say is not going to affect that. So it's just like it was a change of 5. So what it basically means is that now I can choose any function that I want, any basically constant shift or constant that depends on anything that I want except for my own value, and shift it. And a very reasonable constant would be, let's look at the other guys and see what would be their welfare if I didn't interfere in the auction. So if I didn't interfere in the auction, the outcome would probably optimize their own goals. I do participate in the auction, so maybe something else is done. The difference between, so this is actually the difference that I'm going to pay. So basically, I'm actually going to first pay to each player. So the mechanism is pay to each player, as we've said, the total sum of valuations of the others, but then take away the total sum of valuations had we only optimized for them. Okay? So the second term does not depend at all on what I say. It doesn't kill the incentives. But yet, of course, you can see that, of course, had we optimized only for the others, they would get a higher welfare than this case, which optimizes for me and the others together. Okay? And one nice way to look at it is the total payment this way is basically counting what did I do to the others? How much did I harm the others? Okay? Without me, they would make so much. With me, they make less because I make also something. This difference is basically what I need to pay. This is the harm that I cause society. Okay? What's called in economics, basically I've internalized his externalities. So let me just give an example for this. Suppose that we have some kind of network, and this is like a shortest path problem that we learn in algorithms course. I want to send a single message from the source to the destination, and each link has some kind of cost. How much does it really cost to actually send a message on that link? And the question is, how should I send the message from source to destination? So in computer science terms, this is simply I have to find the shortest path between source and destination. What makes it an algorithmic design problem? Well, now the links here are going to be separately owned and with their own goals. So I will have to actually pay them for actually using their link. So of course, now they're going to have some kind of incentive to report their true cost or not according to the way I pay them. What would the VCG method say? How much do I need to pay the links? So the VCG mechanism in this case would say the following thing. First of all, you do take the shortest path. And the shortest path is what's here in green. Total cost 2 plus 3 plus 2 plus 6, which I think is 13. Okay? So this is the first side. And now we have to figure out what is the payment that will actually ensure that I get all these numbers to begin with. And what it says is the following. Let's see how much do we need to pay for this 2 guy on the top. When I get to actually calculating the amount of payment that he needs to get, I basically have to look what would happen without him. What would be the shortest path without this guy? Okay? So without this guy, I think that the shortest path turns out to be 15. So I think it's something like, actually I don't know what, maybe 3 and then 8 and then 5. No, that's more than that's 16. Well, so there is some other path here that does not use the tooling at the top that of cost 15, if the example is correct. And which means that the following thing. With this guy, we have something of length 13, which means that he pays the cost of 2 really, and the others, all the others together, which basically means the other guys on the link pay 11. Without him, everyone will pay 15. So his, if you wish, the amount that he contributed to society is 4. The difference between this 15 and 11, which is what the others, the cost of the others. So he should be paid 4. Not 2, but rather 4. And if you pay him 4 and do the same calculation for everyone, then you're guaranteed, well, guaranteed if everyone is rational, that they will tell the truth. Okay? So this is like an example how you can take like a classic, if you wish, very stylized, but still you can see that it comes up in many places, and try to apply the pricing to it. So this is very nice. Now we have this amazing technique, VCG, from economic theory. We should be done. And in fact, I would say that probably it's true that the first few years of the field was rather basically busy understanding what this means, VCG, and how we can use it in various computer science applications. But for a long time, other issues have crept in. And here are the following example, the following 3 top reasons where we need to do other things and not just use this great invention, VCG pricing. The first problem is the price of, if you wish, revenue or budget balance. If you try to use it exactly as stated, you basically get problems in terms of sometimes people pay too much or too little for things. For example, in the previous example, we have to actually calculate how much are the total payments then to the different links. They can be many times higher than the cost of the shortest path or even the second shortest path or so on. So there's obviously something wrong here where we do get the shortest path, but we pay for it at a price that is much, much higher. Sometimes we have mechanisms where actually you have to subsidize, you have to pay to the bidders, even though that does not make sense. That's one reason. The second kind of reason is the fact that VCG only works when you're trying to optimize what's called the social welfare, the sum of utilities of the players. Many other times, we want to maximize other things, not just the sum of utilities, usually some kind of fairness condition, in the sense that we don't want any single person or bidder to be really in a bad situation, to have a very low VI. So of course, this also applies in economic settings, but in computer science settings, a lot of time when you're doing scheduling, we're not just trying to optimize, to minimize the average completion time, which is like the sum of completion times, but we're also usually trying to minimize the completion time of the last job, the make span. So if that is the case, if that's what we want to minimize, then we can't use VCG because it just doesn't work. It can only be applied to the very single optimization goal of the sum of the VIs. So many times we want to optimize other things. That's the second major reason. And the third major reason is that we can't always do this optimization. So actually optimizing the right allocation in most computationally interesting problems is going to be a computationally hard problem, and we will not be able to do that, but only get some kind of approximation or heuristic or anything like that. And the problem is that if we only have an approximation or heuristic, then we're not guaranteed that the VCG will actually give us incentives, the correct incentives. So to get the correct incentives, we have to do the exact optimization. If we don't do that, we've lost. We don't have these guarantees. So what I'm going to do here in the rest of the time that I have is give a few examples of the kind of places where we have these new challenges and the kind of results that you get there. But before I do that, I would like to try to put in some perspective, what are basically the requirements that we get in order to get incentive compatibility, so I can sort of try to persuade you why what you get is incentive compatible in various results. So basically, an easy proposition can characterize what requirement must the pricing pass in order for the resulting mechanism to be incentive compatible. And it is the following two results needed. The first thing is, if you look how much player I pays, that cannot depend in any way on what he says. Beyond the fact that what he says changes the outcome, and so that's the only way in which the payment can depend on what he says. If I say two different things and the same outcome results, the same allocation results, then it also must be the case that I pay the same amount in both cases. Otherwise, the motivation for manipulation is completely clear. I will just say the thing which makes me pay less. Okay? So this is the first thing that you must have, first condition of payment. So for example, notice that the second price exactly satisfies this. What I pay does not depend at all on what I say, but only on what the other guys say. The second requirement is that the mechanism must optimize for each player. So basically, once now we have prices that only depend on the outcomes, which is ensured by the first condition, now each player basically has in front of himself some kind of optimization problem. How much value do I get from some kind of allocation A versus how much payment do I pay for allocation A? And of course, each player will optimize for that. So what we need to do is that the optimum of this is exactly what the mechanism does if it tells the truth. So the mechanism must optimize basically for each player. And the difficulty here comes from the fact that you're optimizing together for all the different players who are participating, which may have clashing views. And somehow you hope that these payments actually made all these clashing goals the same goal, which you must do. So here's an example of the budget issue. Here's a very simple multicast problem. I have a source that wants to multicast some kind of a message to the different leaves in this tree. And now each leaf has some kind of value that he gets from actually getting this broadcast message, which is written in the different circles of the leaves. But also we're going to have some kind of cost on each edge, which describes the cost for actually using that edge. What we really want to do is basically send a message, send some kind of, decide which part, which subpart, if you wish, of the different players, of the different leaves will actually get the message, and then have a tree rooted that only gets to this subset of leaves, and then do the pricing in a way that makes them correct, that makes it reasonable. Okay, so, and the idea is here that the edge costs are going to be common knowledge. That's not going to be the secret part, but really the players here are going to be the leaves of the tree. So what happens if you actually try to optimize, finding the, basically the subtree or the set of leaves that gives you highest total value, and then you see how much they need to pay, you see that they pay too little. The amount that they pay cannot cover the cost of transmission. Basically, if you look at, let's say, the 9 guys there, how much is he going to pay? So if you try to put some kind of VCG prices according to how much he has to pay, you see that he has to pay very little. Because even without him, the other guys would get the transmission. So really, he shouldn't have to pay for anything but his own edge. But of course, if you do the same kind of logic for each separate player that only pays for his own edge, no one pays for the common edges. So you can't just do a VCG kind of thing here. You have a budget deficit. You don't raise enough money to cover the real expenses. So here's another mechanism, which is like a Shepley cost-sharing mechanism, sometimes called. The idea is the following. You start by thinking, OK, everyone will get the transmission. And then at that point, you say, well, let's see, I'm going to put tentative payments on each player. And what are the tentative payments? Basically, each link is going to be paid by everyone that uses it. So for example, let's look at the 8 guy at the beginning. He has to pay for the 3 edge leading to it completely. And then the 2 edge, after that, he has to pay half of it because he shares it with the 11 player. And then he has to pay 1/3 of the 6 and 1/4 of the 12. So his payment should be 3 plus half of 2 plus 1/3 of 6 plus 1/4 of 12. And if you look at this number, it's more than 8. He's not willing to pay so much. So he drops from the auction. Okay? And at this point, he drops. Now we're left with 3 players. And now we recalculate this kind of thing. For example, if you now do the calculation for the 11 guy, he has to pay completely for the 1 edge, completely for the 2 edge afterwards, because now this guy has already dropped. And now he keeps on sharing the next 2 edges with 2 and with 1 and with 2 other players. At this point, he's happy. So when everyone is happy, no one wants to retire, we're done, and this is what the payments are. Okay? So it's a different kind of payment, sort of fair in some sense. And if you look here, this also is incentive compatible. There is never any reason to lie. If you look what happens, I'm basically presented with numbers, and if I'm willing to pay this, I stay in. If I'm not willing to pay, I go out. And of course, you have to make sure and see what happens, different orders and so on. But this all works out. The prices only increase. The order of considering the different players does not matter. And this is one example of another mechanism, if you wish. Let me skip this example. Let's look at another scheduling example. So this example is we have a bunch of processors that can execute jobs, and we have a bunch of jobs that need to be executed over them. And let me take the most general scheduling problem in the literature, which is for every process and every processor, there's going to be some cost of executing that process on that processor. And these are, this can be arbitrary numbers, or this is like the completely general model of scheduling. And of course, to make it interesting, we're assuming that the processors here are basically strategic. They want to get paid. And their capabilities, how good I am, how much CPU do I have, what is my communication bandwidth, and so on. All this is private for the processor. So the processors know exactly how much time it will take for them, or what cost will it take for them to run each and every job. But now the question is, how do I get them to actually report these times correctly before I do the allocation and send things? Okay? And my goal would be the classic goal, the most standard goal in this whole field of scheduling, usually if you're a computer scientist, which is optimize the make span, the last time of the last job, the finishing time of the last job. And now if you try to look, so this is a problem that's hard computationally, but you can approximate it well in various situations. And the question is, can you do this in an incentive-compatible way? And the main result is, and I won't, so it's a very simple proof, but it will take me 5 minutes that I don't have here, that you cannot do it. So there's no way to assign prices in a way that will make this incentive-compatible with the processors. And even if you try to approximate it, as long as you lose a factor of less than 2, the theorem says that you cannot do it in an incentive-compatible way. And actually, for a pretty long time, nothing was known. Can you get within a factor of 2? Because the only normal upper bound is actually losing totally, an upper bound of losing a factor of n, basically, which means that you really are, n is the number of processors here. So you basically schedule everything on one processor or something like that. And after a long time, the lower bound was just slightly improved. And in general, and by the way, with significantly hard work. And so this is one open problem saying, can you get some kind of approximation? I don't know, 2.42 approximation, or any kind of reasonable, provably reasonable approximation, or even heuristically approximation for this kind of job if you insist on incentive compatibility. So this is another one of the open areas. The third example that I want to show is combinatorial auctions. So let me just say what they are. So combinatorial auctions, they have a bunch of items, m different items, and n bidders are actually wanting subsets of these items. And the whole point is that the value of a subset of items is not just given by the value of each item separately, because there are connections. Maybe a bidder has like a common budget that he can't just take everything, but they are related. Maybe he needs 2 adjacent spots in order for it to make sense. There are many kinds of things. So in general, the general formalization is that the value, each I has a value for every possible set of items S. And we're assuming that these values are increasing as you get more items, which is very natural. but nothing beyond that. And the basic goal would be, let's allocate. How do we auction all these items together? Okay, so you may in general, how do we auction all these items together in a way that maximizes the total value? So if SI is a set of items that I get, how do I optimize the total value that everyone gets together? And there are a bunch of difficulties there if you're trying to look. First of all, there's a representation kind of thing. The number of possible items is small, usually manageable. The number of possible subsets is going to be exponentially large. How can you even represent the value of a bundle? I mean, there are exponentially many numbers that you need to give. Somehow you're going to have to either succinctly express it or have some kind of iterative protocol by which this information leaks out. You're going to have to do something. The second problem is that computation. Computationally, this is like a hopelessly hard problem. Many heuristics that can do pretty well. But again, if you have only heuristics or approximations, you can't use VCG. Okay? And then, of course, the incentives. Once we have some kind of a handle on the computation using some kind of approximation, then we have the problem of incentives. And of course, a classic example of that, but there are many other examples in transportation and many other in procurement and many other application domains. The classic example are the Fcc Spectrum Auctions, where basically, this is what I took from the FCC site about a year or two ago when I stole this slide. This is what they were selling at that time, something like 2 years ago. So basically, each of these, little areas is a license. Actually, each of these little areas is about 3 or 4 different licenses, one in each one of these colors, frequency bands, specified by the colors here. So as you can see, they were selling something like, I think it's like 300 regions times 5 licenses for each region, over 1,000 items together. And the different, basically, cellular companies, and the next time, apparently, even Google, are going to actually bidding on these sets of licenses, which you need in order to operate any kind of wireless service. Okay? And the question is, how do we actually do that? So this is a practical problem. It's actually raising billions of dollars for the Treasury. And it actually has even larger implications in terms of the whole economy, not just the amount of money that the government gets. How do you run these kinds of things? Okay? So again, as we said, computationally, it's an NP-hard problem. You can do many types of approximations or optimizations here in terms of computational settings. So probably if you just want to find a good allocation, there are many things that you can do pretty well. But you can't just plug in the usual VCG kind of pricing ideas to make the whole thing incentive compatible. It doesn't work. You need to find the prices, compute the prices in some kind of clever way if you're only approximating. And then there are a bunch of special cases. So this is, again, one of these things that I don't get here. There are basically 2 strategies or 2 special cases by which we actually know how to get something that's incentive compatible heuristically. But in the general case, but these are very limited cases, and the most general interesting cases are totally open. So I'm going to skip a description of this case, which basically is a case that people understand well how you can get incentive compatibility. And just leave basically, and basically that case says that if you have a single parameter in your problem, single secret parameter in your problem, then you can do stuff. And many cases do have single parameter. For example, the example that I showed, let's say with cost sharing, each participant has a single parameter, which is its own value. Okay? Or in a regular auction of one item, each participant has a single parameter, which is his own value again. So in this case, you can do, there are many mechanisms that are known you can do actually in this case. There's a nice result of Roberts from the 70s that says that in the totally general case, and I'm not going to formally specify what does totally general case mean, there is nothing that you can do except for this VCG idea. So basically, there is nothing that's incentive compatible beyond the trick that I showed you, the VCG trick. But the problem is that almost all computationally interesting problems lie somewhere in the middle. So all types of scheduling, all types of combinatorial auctions, most of the things that you would want to do actually are in the middle, in the sense that it's not a single parameter that's not known, nor is it the case that you have so many parameters that basically everything is possible. There are some restrictions, and basically almost all computationally interesting problems fall within this intermediate range, where essentially nothing is known. So nothing is known in the sense that we don't know how to get any incentive-compatible mechanism that's not VCG, where many times, for the various reasons that I explained, we can't use VCG. And yet we don't know whether this is possible even or not possible. So basically, the main open problem of this whole field is trying to understand this intermediate area. What can you do in an incentive-compatible way? And thank you. I will take a question if there are any. Yes.
So this condition, in order to stay incentive compatible, your payment won't depend on your own
Bid, right. Information, yeah.
Information, right, or the revelation. Also seems to imply that if you are a semi-Byzantine agent who will tell the truth if it's strictly better for you, but otherwise, if there's no difference, will lie, it seems like that's a hopeless problem.
Right, okay. So actually, you're right. So the definition that I took said basically that if you're indifferent between the truth and not the truth, you won't lie. One might also consider asking there to be like a strict inequality, that the truth should be really better for you. And it's not that different. It just makes things a bit messier, but I don't think it changes qualitatively any of the results. Basically, as long as sometimes you can be hurt, doesn't matter that you are always hurt, but as long as you never gain and you are sometimes hurt from that, I think that everything that I showed, even under this stricter condition, carries over. Okay? It just makes, formally the presentation a bit messier, but it doesn't matter. Okay, so thank you.